Today's talk is actually his explorations in this domain, and we look forward to listening to you, Siddhartha, on how to automate mathematics.
Thanks, Rajesh. Thanks very much for the introduction and the opportunity to speak about this. So this talk was motivated by work from Google DeepMind. I'll talk very little about my own work on called AlphaGeometry. I'll start with talking about that, but also about friends. So it was in fact an email conversation with Rajesh which prompted this talk. So I'll talk about AlphaGeometry, but I will also talk about the general patterns which are common between AlphaGeometry and other systems, and about how AI for mathematics can be done. I'm not going to be comprehensive. This talk is not a survey or an introduction. It's rather an invitation to this very growing field. So I'll start with something really elementary, just because for this audience, but just because we want to fix some common examples. So here are a couple of common examples of proofs. Okay, sum of angles of a triangle, well, you know that it's 180 degrees, but how is this? So consider a triangle and the key step ABC, and key step is to draw a line through A parallel to BC. Okay, and now you can see that interior opposite angles, these two blue angles are equal, and the two red angles are equal, and the sum of the three angles at A is 180 degrees or pi, hence the sum of the three angles of triangle is also 180 degrees. Okay, so the picture and the proof is from Wikipedia. So another elementary proof, and again a very old proof, that there are infinitely many primes. This is equivalent to showing for any n, we show there is a prime P such that P is greater than n. Okay, and the key idea is to consider the number n factorial, where we all know what n factorial is. Sorry, consider the number n factorial plus 1, and let P be the smallest prime factorial of n factorial plus 1. Okay, so let me just say it in words. You pick the smallest prime factorial of n factorial plus 1, and if this number is less than n, then it divides n factorial, so it cannot divide n factorial plus 1. So it's a prime greater than n. Okay, so those were two concrete examples. My point is to make some general points which are very well known. The reasoning or proving has two components. There is intuition, which is based on analogies, associations, etc. So they are used for these auxiliary constructions, like drawing that line, or considering n factorial plus 1, or even considering the smallest prime factor, which theorem or definition to use. And in more complex proofs, what are the intermediate steps? What are the intermediate lemmas? There are not rules that tell you these are based on intuition. And then there is logical or algorithmic component, which are the deductions and computations. Okay. Intuition is based on tacit knowledge, that is things that we know but can't tell, like riding a bicycle or swimming, and this is acquired by learning through experience. Perhaps you have to learn it through experience because these are high Kolmogorov complexity. That's irrelevant for the rest of this talk. And a counterintuitive fact which is related to what's called a Moravec paradox is, in raw computation power, intuition is actually much harder. Okay, Moravec was mainly talking about sensory motor tasks, but including vision and so on. So we tend to think of logic as harder and intuition as easier, but by an objective measure, which is computational power, intuition is very hard, which is why the intuition side of reasoning did not exist really till little more than 10 years ago, because there wasn't good enough hardware. No. So this is a rough sketch here. Yeah, so this is just a rough sketch, and there's no precise thing. So Daniel Kahneman has something called system 1, system 2, which is commonly had. So intuition is system 1 and logical is system 2. It's not well defined, but roughly we all understand what it means. There's a general sense that these are the two sides. Okay, so with this background, let me come to the actual first star system, AlphaGeometry. This is a remarkable system. It's an AI level system that can solve geometry problems. Okay, and more precisely, it can't solve all of them. You have to write them in a particular language, in a symbolic way. And it can solve those geometric problems which can be expressed in this language. 75% of the Maths Olympiad geometry problems can be expressed in this language. So it can only attempt those problems. But very remarkably, and this is the first system that handles these kinds of creative, intuitive problems at skill level, it manages to solve these problems. If you look at its scores on these problems only and compare it with people who wrote those, its average score in these problems is between the average score of all the silver medalists and gold medalists. In fact, it's very close to the gold medalists. It's a little below a gold medal quality in IMO, which is way above me, for example, and above most people. So AlphaGeometry, it's a few weeks ago. Yeah, so this is a very fast moving field. This is a paper in, I forget, Nature or Science from Google Research, actually, Google DeepMind, but the Google Research Half. It was a few weeks ago, and it's, yeah, I don't know off the top of my head. You mean geometry problem which can't be? No, I don't actually know. I shouldn't just say off the top of my head. Yeah. So I'll say something about the language, but I don't know. It's a very fixed language. Yeah. Okay, so how does this system come about? And this is related to the pattern I said earlier. There is one component of this which is what they call a deductive database plus algebraic reasoning to chase down ratios. This is a powerful and efficient deductive system for reasoning about geometry problem. This is extending earlier work. You can say the work has been all 70 years of computer science is building towards this. Data structures, algorithms, symbolic AI. So you have better and better way of deducing things. Okay, but these are fixed finite deductions that you can make. They increased efficiency on previous work, but this is a continuous growth. And a language model that suggests the auxiliary constructions like drawing that line, or in other contexts you would say n factorial plus 1, but we don't yet have things in other contexts. So in geometry, the auxiliary constructions, there are no rules to tell them and there aren't good systems of rules. You use a language model. The third component is the most important, which is, well, I said language model and I'm not going to explain them. We will treat them as black boxes. Where do you get data to train it? You could take existing problems, but there are hardly any. So the biggest contribution of the people doing this work was the generation of synthetic data to train the language model. In fact, this is what took the most computational effort. I will say what this synthetic data is and how they generate it. So the crucial point is you have a pair, the intuitive system and the rule-based system, algorithmic system, and you generate data. So you have to extract or generate data to train the intuitive system, and a lot of it. Okay, so first, what is the deductive database plus AR? So in the deductive database, you have efficiently represented a finite collection of points and relation between points, lines through them, etc. For example, perp ABCD says the line bit through AB is perpendicular to the line through CD. Okay, so there are 10 to 15 such relations. Some are dependent on others, so I can't say precisely what they have. And rules of deduction, let us deduce consequences of these. This is open source, fortunately, so you can just check. There are 43 rules of deduction that are there in AlphaGeometry. In addition, some things telling you that, say, perpendicular is symmetric and transitive. But the explicit rules of deduction like this. For example, if AB and CD are both perpendicular to BC, then they are parallel to each other. This is one of the rules of deduction. I mean, there are a bunch of rules of deduction of these form. Okay, and what the deductive database does is by iterating deduction with all the rules that apply, you get more and more consequences. At some point, you stop getting new consequences, so you stop. So for a fixed finite set of points, you don't add new points here. But you can deduce everything which you can deduce without adding new points with the rules of, yeah. They're fed as axioms if you wish. They're treated as axioms by the system. It's a domain specific system, so it's not embedded in a larger logic, but they are the axioms of this system, exactly. And there is one more side of this, which is their algebraic reasoning for chasing ratios and so on. So AlphaGeometry deduces from algebraic relations for angles, lengths and ratios. They all turn out to be of this form, A plus B is C plus D, and so you can represent them in matrix and use Gaussian elimination. So one of their contributions is improving the DDAR, the deduction engine, to make it fast. The improvement is important because synthetic data uses these millions of times, as we will see. Okay, and now the main contribution. Where do they, yeah. No, so just that in geometry proofs, you often have this plus this by this is this by this and so on, and you have to deduce using that. Yeah. So if it's a ratio, you take the log. If it's angles, you take the sum. But from their rules of deduction, any relation they get can be written in this form: A plus B is C plus D. Yeah, thanks. So I didn't say that. Thanks. The ratios you can't. It won't be a sum of ratios. It will usually be a sum of the logs of the ratios for which you have the relation, and using that you can deduce with efficient algebra. That's all. This is really an efficiency gain, not a fundamental gain. So the synthetic data, how do you get data to train the language model here? So you take millions of random configurations of points. Here a configuration means a finite set of points and a bunch of relations between them. So for any, you choose how many are perp and parallel and this and that. Okay, so millions of these, and then all the theorems were deduced from the initial configuration. They found 100 million theorems. For each of these 100 million, you traced back to the minimal proof. Fine, so far so good. But now this is what we always say in mathematics. What is a non-trivial theorem in mathematics or any applied mathematics as well? It's where the proof contains something that the statement did not. So in this particular case, if the proof contains a point and the statement did not, then you have to have an auxiliary construction introducing that point. And these auxiliary constructions are noted. Okay, and then a language model is trained on this. I'm going to treat these as black boxes, as I said. In fact, pre-trained on all proofs, for those who know, and fine-tuned to predict auxiliary constructions. So there were two phases of training. Okay, so this is what gave it. Just to clarify, they said no IMO problem was exactly as such in the synthetic data. So there was no copying the full solution. It was exactly with the previous deductive system. No, so you threw away points. Thanks. So I should clarify that. So you have a theorem. So you started with 15 points. Maybe you started with 5 points and some relations between them. And you deduced all theorems. It turned out that some theorem statement involved only 4 of those 5 points, but the proof involved all 5 points. In which case it becomes a statement about those 4 points, and the construction of the 5th point is an auxiliary construction. Yeah, so thanks for the question. That's the clear point. That is you created the whole proof and then just observed that this point was never used in the statement but used in the proof. So we have to introduce it with an auxiliary construction. So the same deductive system can give you synthetic data. These are the key ideas. We generalize to many contexts, but key ideas in this system as well. So given these, how does the system work? No, so you have a statement of a theorem, and that statement of the theorem involves certain relations. This is perpendicular to this is this thing, and so and so. And you just note what points are present in that statement. Just purely what is part of the logical statement. Logic in this restricted logical sense. Oh yes, yes. All these principles extend everywhere beyond mathematics in some sense. I mean, this principle that you can use a deductive system to generate synthetic data and use that to train an intuitive, that's the point of this alpha geometry and friends. The general principles are very general, and that's why I meant, yeah. It just means that, so they generated synthetic random configurations. Just by chance, they may have generated exactly a problem that appeared in an international maths Olympiad. They post-checked with their data and found that did not happen. If that happened, you will worry about contamination, that it has learned from that. If it happened only in one problem, you would exclude that or something like that. As it turned out, there was no contamination in this sense. That I don't know. Yeah, so some of these details, actually they're not even in the paper. Okay, so some of these details you'll have to look at the paper, and some other details I've looked at the paper and looked at the code and even asked the authors on Zulip, and I still don't know. Okay, so some of these things are not documented anywhere. They have some sketch in their paper, but I don't know exactly what is the distribution, for example. But if I'm not mistaken, that level of detail is not even in the paper. So it's not just that I don't know, but it's not even known publicly. Yeah.
So from each configuration,
yeah.
multiple theorems.
Yes, yes. They got lots of theorems. So you trace every theorem.
So you trace every possible theorem?
For every configuration. So it's not per configuration that you're doing it, but per theorem. You generate configurations and you generate theorems. But once you have generated them, it's the theorem that is important. Yeah.
I was trying to understand. So every theorem in this, you have a language where every theorem is a set of points and relations.
No, so every theorem is a series of deductions which starts with some assumptions that these points are parallel, these are perpendicular. It uses the rules of deduction and concludes that something is true. I'll soon give an example that will make things clearer. Yeah. The language model is pre-trained, as I said, on all proofs in the language, and then it's fine-tuned for the task of predicting auxiliary constructions. There are 71 possible auxiliary constructions, which is already part of the language. Yeah. Yeah. Again, some of these details I don't know, and some of these details are not even public. So, some it's my fault that I don't know, some are not even in the paper. Yeah. I'll come to an example. Maybe we can return to these, but because these things are clearer with examples, I have an example slide, which from their paper, in fact. Yeah. Okay, so how are the problems solved? So it's the next slide, not forward. So given a geometry problem represented symbolically, that is something is perpendicular and so on, all deductions are made using this. And if they solve the problem, wonderful. And a few IMO problems they actually solve. Even older systems solve. But if they don't include the auxiliary conclusion, then the language model is asked to suggest candidate auxiliary constructions if they don't include the final conclusion. And for some or all of the auxiliary constructions, suppose we pretend only one auxiliary construction is suggested, you make that and then make deductions based on that. And you keep repeating this process. In practice, so if you assume that at each step one auxiliary construction is suggested, then you make the construction, deduce everything, make the next one, deduce everything. In practice, it suggests a collection of them with weights, and so you have to do some kind of search. What they do is they use what's called a beam search. They actually experimented and said it's quite robust under the nature of the search. So I won't go into any details of this. One, because this is kind of classical, this kind of searches in computer science, and two, they themselves say that's not important. So as I said, the language model is important, DDAR is important, but the most important is the synthetic data. Okay, so here are two pictures. This will, I hope, clarify things. Here is the simple problem they say. Let ABC be a triangle with AB equals AC. Prove that angle ABC is BCA. They try to deduce and you won't succeed in deducing anything from this. Until you make that crucial construction. You take D to be the midpoint of BC. So you add the midpoint of BC and then you drop the line AD. Well, you don't actually drop the line because any 2 points have a line in their language. But what you do is you add the midpoint, and note that when you add the midpoint, you get BD is DC as a consequence and BCD are collinear as a consequence. So any auxiliary construction comes with the consequences. It says this is a point and this point has these properties. Okay, so now once you make this auxiliary construction, it is easy to deduce these two triangles are congruent from the hypothesis, and this angle is equal to this angle. So one auxiliary construction, it deduces from there on. This is the system. And here is an IMO 2015 problem 3. It involves 3 different auxiliary constructions. All these examples were midpoints, but as I said, there are 71 different auxiliary constructions, so there are lots of different things. 3 different midpoint constructions and a whole bunch of deduction that gets to these points. Okay. So this, no, all these are, well, has it discovered a new theorem in mathematics? No, it hasn't, but we don't generally try to discover new theorems in Euclidean geometry, right? So that's, I think, the main reason. I think it has no inherent limitations. So within its domain, IMO problems are probably the hardest problems any human is trying. No human is doing research on Euclidean geometry. So it's a very important question. Is it discovering new mathematics? And I'll talk about other systems that do discover, less powerful, but they do discover new theorems. But here I feel one reason it cannot discover new theorems is, exactly because nobody actually does. It's not an active area of research, Euclidean geometry. Yes. They have circumcircles, incircles, and so on. As I said, there's 71 of them. If you open the code, I won't open the code now and see, but it's open sourced, so you just have to read. Yes, that's right. I don't know if it found new proofs of the IMO problems or every problem some candidate or the other had found. Yeah. This picture you're saying, yes, both of these are exactly given by AlphaGeometry. Incidentally, it's a remarkably lightweight system because after this thing, it runs on this, my laptop even. It can actually run on a laptop and not just this, it can give some non-trivial theorems there. I don't know if it can run the bigger theorems on a laptop, but Yeah, because the model is only some 300 million parameters. It's not a large language model. I mean, yeah, it's today you'll not even call it tiny. You'll call it micro or something. Yeah.
Looking at that last line, which is about 109 or 189 steps.
Yes.
Is this step language, proof language very verbose or?
No, I think that's because IMO problems are hard.
That long?
Yeah. Yeah. I mean, yeah.
So just to make sure, does it come with a guarantee that this proof is?
Yes, yes. Assuming you trust the axiom system. So they're using a bespoke axiom system. They did talk about this, and I will mention these things. You would rather want it to embed in first order logic or an interactive system that you trust, but they just used it. So if you trust that their deduction system is correct and their auxiliary, so they make auxiliary constructions. They're just saying we are going to construct a point with this property. Maybe that's impossible. So if you trust their deduction system, these proofs are correct. No, so you say it cannot be I mean, it's suggesting auxiliary constructions. So I assume that some of the auxiliary constructions will be useless. And it is possible that hallucinations in the sense that auxiliary constructions may have invalid syntax, in which case you just reject them. So the great thing about passing through a deductive system is that there are no hallucinations that escape the deductive system. You just throw them away. I mean, so the only hallucination you could have here is something suggesting making an auxiliary construction which doesn't exist. And I would guess that it does make such things which are simply rejected. Again, it's not something that is mentioned anywhere in the paper, so I cannot other than guess. Yeah.
So I would rather take an example from the first one.
Yeah.
So in the first problem, where
Yeah.
an isosceles triangle,
Yeah.
would the language model suggest construct a midpoint of PC?
Yes.
Or would it suggest construct a midpoint PC such the following two?
No. It suggests construct midpoint BC. The first line is what is the language of the thing, and in a certain file in the thing it says that midpoint DC has these properties. Yeah, thanks. So, yeah.
Problems where it fails, if you ask the question again, what is it?
I don't know. Again, you can experiment. It's open source. What happens, and also it's, you see the two systems are decoupled. So you can only run the language model part again and again. Are there problems where it deadlocks? What happens if you, I don't know. It probably fails, otherwise they would raise their rate by, if there's a simple fix, they would raise their rate. But more details than that, I don't know. Okay, so let's get to friends. This is a section I'm going to skip except for a summary. So the last component I didn't talk about, which is large language models, and I'm going to treat them as a black box. Just except for mentioning what abilities they have. So they have remarkable abilities roughly corresponding to intuition. They can reason by analogy, and very importantly compositional analogy, not just a simple analogy that this is this, but many components are analogous to different things. They can mix and match. So compositional analogy or compositional generalization is one of their superpowers, and the other superpower is natural language, because natural language not only makes interaction with them easy, it makes them have access to our human literature as well, and that is crucial in these cases. They are familiar with a lot of stuff, but they can also combine broad knowledge with specific knowledge from their input. Okay, what is called in-context prompting. Yeah, so that's why they hallucinate, that's why they sometimes get things wrong. So it's not perfect at any of these things, but it has roughly, I'd say, almost human level natural language ability. So I don't, but they can handle it rather well. I mean, so yeah, so. But they are terrible at avoiding logical fallacies and judging correctness. This is the weakness here. Okay? Yeah, they're terrible at avoiding logical fallacies. They tend to output things which are logically rubbish, and they cannot look back at their solution and tell whether it's correct or not. I'll come to that. So this is their big weakness. They have many strengths. So pairing them with deduction and checking systems is the natural way to build things. And many systems, as you see, even AlphaGeometry is built on that. Okay, so I'll move to more examples. Okay, so here is a new mathematics result, not a terribly interesting mathematics result, but a new result called the cap set problem, which was solved by fun search. Okay, so there is the cap set problem is to find the largest possible set of vectors in this finite field Z mod 3 to the n, a vector space over this finite field, so that no three vectors sum to 0. So geometrically it's like taking the points at 3 points by 3 points by 3.7, n equals 3, and choosing a set of points so there are no lines. Okay, this is an important problem, and apparently Terry Tao called it a favorite problem and so on. So it's a much studied problem in extremal combinatorics. So exact results, so you could try to approach this by brutal enumeration, but up to n equals 6 only we have exact results, and beyond that neither theory has given the best result, nor has, and brutal enumeration cannot go beyond this. Okay, but a system called Fun Search from Google DeepMind found a construction for n equals 8 which was the best construction to date. So this is a new mathematical result. As a result, it's a new lower bound on the size of this set. Okay, it's an explicit construction.
Can you say best as in so far?
Best so far. Beat the record so far by a fairly big margin. So the best so far. Okay. Yeah, it doesn't mean it's provably optimal. In fact, it's not, so far as we know. Now, the interesting thing about this, again, like AlphaGeometry, a very generalizable system, it did not find a cap set. Instead, it found a program to find this set. Okay, I'll be a little more precise. It did not, so it does a evolutionary search. This is an old idea. Okay, but in fact, most of the program for generating cap sets is fixed. It's what's called a greedy algorithm. You pick a point, then you pick what looks like the next best point to add, and so on. Keep adding the best point you can. Best based on a function which is called a priority function, and this priority function is learned. So it's learned by evolution. You start with one handwritten priority function based on what somebody thinks is a good idea, and at each time we have a population of such functions. We evaluate these functions, choose the best, and combine to get new functions. This is an old idea. It's used for traveling salesmen and so on, but when you're using a usual evolutionary algorithm, what do you mean by combining? It's easy to combine paths, words, etc. How do you combine functions? That you can't do normally, but this is one of the powers of the language models. You use a language model. This is Cody from the Palm 2 family. This is the previous best, not the Gemini from Google, their code-directed thing. You give it instructions and you give it example functions, and it generates a new program for you. Of course, some of those will be worse than the original, and some of those will even be wrong, but this is a way in which you can evolve things by having it. Okay. Indeed, as you see, this method is entirely general, and they did use it to solve some other more practical optimization problems. You can try to have an evolutionary algorithm to search for basically anything using this philosophy. Another, which I like a lot, which I think is maybe most practically useful, symbolic integration, finding the integral of sin x plus cos squared x or whatever else you want to do. This is work of Lampel and Francois Charton. Charton has a lot of very nice videos and papers about these and related things. So language model was trained to symbolically integrate a given function. Again, same story. You want synthetic data, and there are three forms in which they generate it. First is you cheat. You know, Mathematica is rather good at it. Just get it to generate random functions and try to get it to integrate. If you have got it, you have got this. Okay. But then the result will still be better than Mathematica raw. But this is not very generalizable because it depends on existing systems being good. More interestingly, we know that integration is the reverse of differentiation. So you randomly generate a function and differentiate it, and then you know integral of f is f. This one can do, and it's very nice. The problem is that distribution is a little bad, in that you'll tend to have short functions with long integrals, when in practice what you got is a relatively short function whose integral is long, and that's why you could not find it. Okay, and these people have a really nice idea to do it synthetically, which is called backward generation with integration by parts, which I'll explain. So you pick random functions capital F and capital G, compute their derivatives little f and little g. Do it at a stage where you have already done a bunch of backward differentiation. Now if little f times g is already in the training data, then we know it's integral. Okay, that is because little f times g is, you use backward or something to generate it. And then you can compute the integral of capital F times g by integration by parts. And then I find that the distribution you get if you do backward generation and then do backward generation with IBP is of the correct nature. because this is often a longer function, the integral, than the left hand side. So you get synthetic data with which you can train this. Okay, they have used similar approaches for all sorts of things, solving ODEs, solving recurrences, and so on. The general principle here is you're often solving in mathematics inverse problems where the direct problem is easy. Solve the direct problem with randomization to generate synthetic data, and then you have train your model. This is the story. No, they actually calculated distribution. I think it's roughly uniform. I don't know the exact details, but no, they're not eyeballing. They calculated the frequency, the length, or whatever frequencies of the two sides, and did it. I'm reporting a qualitative statement they made. I haven't looked at the quantitative data, but the authors did look at it quantitatively. So yeah. Short just means when you write it on paper or in a computer, it's short. Yeah. So that's okay. So I'll have to make a little bit of a digression now. So we have looked at some systems before going to the new ones. Yeah. No. So here these two did not use any real rules of deduction, just computation. Yeah. So symbolic algebra, not numerical computations, but just symbolic algebra. So that's the point, thanks. So that brings up to the new thing. So if you look at these three systems, one of them used a restricted rule of deduction just for geometry, and the other two did not really use deduction at all. They just used symbolic algebra. Okay, one used computation. No, these are the friends of AlphaGeometry and friends. Yeah. So I'll be not talking more about AlphaGeometry, I was talking about various systems of doing things. Okay, so these use rather specific things. What if you want to do general mathematics? One way is SAT solvers, and also their more general counterparts, SMT solvers. Just to point out, so SAT is the original NP complete problem. It is given finitely many Boolean variables, true or false. Can you solve them? And you have equations involving these. Can you find a solution for this? So Cook-Levin theorem, any problem in NP can be reduced to SAT. But the important point is in practice, lots and lots of problems can be reduced to SAT. So the clever idea computer scientists have developed is that you map lots and lots of problems to one problem and work hard at solving this problem very, very well. This works very well in practice. One mathematical example is this Boolean Pythagorean triples problem. It was stated in the 80s by, okay, I'm forgetting for a moment. But it was stated in the 80s and solved a few years ago, in 1916 or so. It is, can you color the integers in two colors, red and black or red and blue, so that if you have a triple like 3, 4, 5, which are three sides of a right angle triangle, or 12, 5s, 13, then they cannot all three be the same color. Okay, it was found that up to 7,500 or so you can, and beyond that you can't with a SAT solver. Okay. These are examples of these. This is more general logic, but this still works for only finite problems. For general problems, you have resolution theorem provers. They involve this thing called unification, where you find correct substitution. They can solve problems in first order logic, and first order logic is in principle all of mathematics. In practice, these solvers work only if the proof depends on a small number of axioms, but they're still powerful system. So one example here is Robin's conjecture. This was a characterization of Boolean algebras, that is the structure of true and false, in terms of commutativity of the OR operation and one single equation. So it's a commutativity and associativity of OR, and this equation gives you all the other properties of a Boolean algebra. This was conjectured in 1930s. Okay, and Tarski students worked on it and so on. So it was considered an important enough problem for many decades. It was solved in 1996, William McCune's automated theorem prover EQP. Now some of the ideas of this, like discriminant trees and so on, are still heavily used in the interactive theorem proving systems, which I'll come to next. So in practice, first order logic is very poor for representing a large body of mathematics. For those in more computer science background, that's why you have scripting languages, you would say, as against something with OOP or whatever else. Managing complexity is different from local reasoning. So first order logic is very good for local reasoning, in principle for everything, but in practice no. What you use are interactive theorem provers, software systems where proofs are obtained by human machine collaboration. So the computer both finds proofs and verifies correctness. And with these, mathematics can be digitized on a large scale. In particular, lean theorem prover is the one that is heavily used in mathematics. Its library includes most of undergraduate mathematics and now many advanced topics, including many theorems proved just a few weeks ago and so on. So what is the value of this? There are many uses of these, but one is they can give you a superhuman level of correctness. The one issue is, why are you trusting these interactive theorem provers? You don't have to trust the whole theorem prover. The part that checks the proof is called a kernel. It's a small amount of code, hopefully well documented, and it's all open sourced anyway in today's era. So the analogy here, which is a bit of an oversimplification, is chess engines are huge programs, but the part that checks what is a legal move is a much smaller program. So that has to be correct so that for all the moves to be legal. So similarly, checking this. And even better, Leo de Moura, Lean's creator, is very particular about these things. Even better, you can write your own proof checker, an independent kernel. As of today, with Lean 4, there are 2 other kernels written in Lean, and then 1 more written from scratch in Rust. So there is a completely different kernel which checks your proofs. So there is, really you can trust these proofs. And if you really are paranoid, write your own kernel. Okay. But in addition to correctness, which we really don't care that much about because nobody died because the theorem was wrong, there are other benefits from this, which is collaboration does not require trust between collaborators. So mathematical collaboration is limited because somebody gives you a proof, you have to check whether it's correct unless you really trust that person. And it also means people with local knowledge can't use it because things are often stated slightly wrong and they will prove things correctly. And we can even collaborate with knowledgeable, imaginative experts whose proof we absolutely cannot trust, like large language models such as GPT-4. I wasn't about to insult someone even though it looked that way. Okay, so now I'll turn to some other systems involving interactive theorem provers. The draft, sketch and proof, which came about a year ago, it gives formal proofs, that is proof which can be checked by a computer. You give it a statement, it does it. And the way it does it is it uses a large language model to generate an informal sketch of a proof. It's translated into a series of steps so that the problem is broken into sub-problems. Concretely, the proof was written as a series of statements in Isabelle. They used Isabelle, not Lean, because it has better automation as of today. So what you did is it gave a proof, it wrote it as a series of statements and used rule-based automation to complete the proofs. This is a typical pattern that you have. And it had decent success rate with high school mathematics problems. What if you want to go to a larger scale proof? Well, you can try to translate. At this point, I'm being speculative, but it's kind of obvious what you would want to do. You can try to do it iteratively. That is, translate step by step. Where it fails, you can backtrack. And to do this, you would want to translate to structured proofs. You may want to add details. You can put knowledge in the prompt, which works very well with language models. You can guide using heuristics, etc. For this to work, you need 2 things. And I'll give demos of GPT-4 doing these things to different degrees of success. One is you need translation to formal systems to have high accuracy because you're going from an informal to a formal proof. And the proof generation by language model itself has to be good enough. If you do that, you can hope you'll generate an informal proof, which is going to have a lot of rubbish, but you will keep checking it and feedback and iteratively improve things. Oh, okay, so here's the demo of the translation part. This is a system of myself with a bunch of collaborators, including Anand here. This is Lean, except that I'm typing in English, because let's say I don't know how to write. There are infinitely many natural numbers. It has started working now. And the language model, it goes to GPT-4. Language model suggests a translation where you can replace it. Okay. This is of course a much less impressive system than what I said, but I can tell you the insides of it since it's our own system. Okay, so this is a system we call Lean-A. How do you get good responses from GPT or 4 or whatever else from a language model? So suppose we are given the statement of a theorem. We find, let's say, 20 statements that are similar to it, and these are documentation strings in the library, so we already know their translations, and we include them in the prompt. And then we query GPT-4 and ask for a bunch of responses. And then we discard responses that are not valid. This is like a question of hallucination. So there will be hallucination, you throw away things that are not valid. And because Lean is a very strict language, generally if things are valid, the chance they are correct is reasonably high. Okay? These are not so easy to fake. So here's an example of a prompt. If a vector space is two-dimensional, then it's finite dimensional. This is only an excerpt from the prompt. You give a system prompt, and then I say the user said this, and the assistant replied this way. These are examples. I give 20 such examples. Finally, I said the user said this, and you as assistant, please reply to me. And the assistant replied by translating it into Lean. This is quite a complex statement actually, but it manages fine. So these were one of 40 silly statements we used. We used a bunch of silly statements to test, but when you test, you're always worried about contamination. Has it already seen this somewhere in the literature? Well, you can be pretty sure nobody in the literature is going to write a proof that if a space is two-dimensional, then it's finite dimensional. It's far too silly to do this. So this was one of the tricks we had. We also had 40 theorems and 40 false statements in our test set. Originally we used codecs. When we went to GPT-4, we found a certain phenomenon. We had to exclude from our results a few statements because when we asked it to translate some of these false statements, GPT-4 just said these are false instead of translating them. Okay. So anyway, out of these 120 examples, we had success rate of 85%. These were relatively simple. So it shows that translation can work at least in simple cases. Okay. So how can we try to improve it? However, this success rate was below 50% for ProofNet data. And there are many causes of failure, typically notation, but one that I did not guess till I actually looked very carefully at the examples and failures. So this ProofNet standard, it took a problem from Rudin, and Rudin perversely uses the term condensation point, where more reasonable people will call it accumulation point or limit point. And MATLAB indeed uses accumulation point. This means prompts go wrong. Okay, so we need to translate, so this has to be corrected for. We also need to translate statements whose translation is not a single statement but a block. Okay, and so I go to my final part. I'll be a little brief here. So we can attempt address all these issues using GPT-4 for auxiliary tasks. And this is the last set of slides. I'll be quicker than I intended for this. GPT-4 examples, just to show you here. So suppose we want to correct the fact that something used condensation points. I can ask GPT-4 to tell me all the mathematical terms and tell me all the synonyms, and then look up in the library and find I have had the terms in the library. So I look up in the library and find that the library uses accumulation point, it doesn't use condense point, so get GPT-4 to translate. Okay, so these are examples of when you think of using it, you don't think of one shot getting the answer from the language model. You break up into lots of tasks and lots of auxiliary tasks it does really well. Okay, here's another example which I will go through very quickly. So this is code in Lean code which I wrote as part of my own course. It finds the smallest element in a list which is non-empty and proves two properties of it. That's it's in the list and it's less than or equal to the elements in the list. Okay. One thing about this is, and I just ask it to describe no examples. This is what's called zero shot. And it says it defines a function and two theorems. It gives a correct description of the statement and it also gives a correct description of the theorems. So this is again a task it does very well. Just in case you thought GPT-4 only copies, this is clearly not the case. This won't be anywhere on the internet. Okay, so now quickly some examples. So I asked it some simple linear algebra problems. This one it gave 3 solutions, interestingly 3 different solutions. Can ignore this. Then I asked it this problem and I was a bit embarrassed when it told me that I had formulated it wrong. It gave a counter example. Then I formulated correctly a somewhat non-trivial problem. You take a square matrix, prove that if A cube is I, then A is diagonalizable. If you don't understand, this is the sort of thing we'll ask incoming PhD students. And GPT-4 answered. And indeed, I was talking to friends, and friend Shaunak pointed out, this is something we really had asked our incoming PhD students, and anyone who answered was selected. Find all 2 by 2 matrices with rational entries such that a to the 5 is I. This is a mix of linear algebra and some number theory. And indeed, GPT-4 gave a 2 by 2 matrix, and it started by noting the minimal polynomial, a degree of the minimal polynomial, and then verified these things. And then I realized that, as I would with a student, it had used a non-trivial fact. So I said, you use this, prove it, and it proved it also. So it's pretty impressive in these cases, but not so impressive in other cases. I asked an analysis question, which I had again asked incoming PhD students, and based on this answer, I asked a simpler question, and it persistently gave wrong answers, even though I tried to guide it. And it kept trying to use every increasing sequence is unbounded, which is false, or assume the maximum is attained, which is also false. So kept using these, okay? But if you asked it to prove or disprove, it gave a counterexample. So it knows it's false, it still uses it. This is what I mean by it really doesn't try to be logically consistent. Interestingly, another model, Mistral Medium, was much better at such questions. But overall, I think GPT-4 is still better. Yeah. So part of the reason I think it's so bad at these analysis questions is so many people, especially in America, are forced to take calculus courses. There's just a lot of garbage on the internet of this nature. Yeah. A side point is smaller models work for auxiliary tasks. Here's another example, and I won't go into any details of this. Let me just point out though, in its third solution, in fairness to it, it proved by contradiction saying that something must be 4, but it is 4. Therefore, so and so. So when I said it's terrible at judging correctness, I don't think I've met a student yet who gives a proof by contradiction based on 4 is not equal to 4. So it can be very impressive, but it can give garbage. You have to filter out and do it. Couple of other auxiliary tasks it does very well. This one I found in the wild. It's actual statement from a paper of mine, exposition, about metabillion groups. I said, due to lack of time, I won't say much, but just if you want to see the slides later, you can see them. By the way, slides are on the internet, but it managed to give details very well. This is important if you are trying to automatically translate from mathematical texts, which may be at high level, to lean or something like this. In fact, I was quite impressed with, I thought I would have to give it examples, but with no zero shots, it picked up all sorts of subtleties. It messed up this formula, but if you do it iteratively, it would probably get it correctly. And another auxiliary task, we would want, when I say iteratively, step by step, what are the steps? You would want some kind of structured proof. So I realized that maybe the best way, instead of teaching it a structured language, is go with a language it knows very well. Those who are familiar with computer science will recognize this is JSON, of course. I tell it that everything is, every state, make a list. Every element in the list is either an assumption, observation, theorem, or an assertion. An assertion has a claim and justification and what it uses. And it can do this very well. So these are all the ingredients that are there. Okay. So with this tour of many things, let me summarize. Language models can be used for many core and auxiliary tasks due to these abilities. But due to their unreliability, it's natural to combine them with interactive theorem provers. A comment here, this book I was reading by Andreas Wagner, who's an evolutionary biologist. So a more general lesson, are they creative? So a definition widely used among psychologists apparently of creativity is finding original and appropriate solutions to a problem. Language models try to find an appropriate solution. They're certainly original. They are, however, they try to find appropriate by analogy and so on, but they're very poor judges of appropriateness. So they can match creativity provided a problem is either easy enough or the notion of appropriate, like poetry, is flexible enough. But with a filtering by a deductive system, maybe you can get the both parts of creativity. The last comment I'll make is, while we are talking about automating mathematics, really what we want in the shorter term is to combine AI, language models or whatever next form comes, interactive theorem provers and symbolic algebra, Mathematica, Sage, etc. to actually make tools for discovery, formalization, and learning of mathematics. We don't just want to keep working for 10 years from now or 100 years from now when things get automated. We want to help people on the 3 to 5 year time scale, let us say. I think that is reasonable. So I'll end with my last thank you slide, which is my wish list or to-do list of things that can be worked on. Okay, but I won't go into detail. Thanks.
Thank you, Siddharth. For the audience, actually every one of Siddharth's lectures in his class are like this, intense and fast, and you have to be really on your toes to be able to catch what he's saying. So over to you all now for the questions.
See, so it's very non-uniform depending on the area, partly based on who is, on what is easier or harder to formalize, and partly based on who, but mostly based on who has got into the business. So on the algebraic side, enormous amount has been formalized because perfectoid spaces are formalized. The Fields Medal level of work and everything building up to that. On the other hand, algebraic topology is only now being formalized. Probabilities and analysis, particularly complex analysis, are getting much better. So it's highly uneven. In some areas of mathematics, it's gone well beyond the first year, and in other areas, it is lagging. So one of the tricks used is you have a grand challenge. You'll formalize this or that, and everything such as the background gets automatically formalized. So sphere reversion was using H principles was a grand challenge that was achieved. So differential topology is formalized, but not that much Riemannian geometry. Complex analysis is a little complex analysis. Terry Tao is leading an effort to prove the prime number theorem and a bunch of other such results in analytical number theory. Terry Tao and Alex Kontorovich, I should say. And so that means over the next few months, a lot of it will get formalized. Yeah.
So, example of reducing condensation.
Right.
A similar example is, I think, Hoffman level says ideal value.
Yeah.
Says characteristic value.
Yeah.
Is there, can we say have a dictionary of sorts?
Right.
Thesaurus of sorts.
Right.
So does that?
Yes, you could try to build it up. What I actually did in advance, and by the way, I should thank Microsoft for that. It's because of funding from my cloud credits from Microsoft, not funding in any other sense, that I could run so much on GPT-4. So what I did in advance is I took every documentation string, there are 40,000 of them, and told me what are the mathematical terms in this. Okay, so now you give me a statement which involves condensation point. It fails to translate. Then I can extract condensation point and all the synonyms and look for those synonyms in this pre-built list. So what you are saying is, can we build a dictionary of thesaurus? We can try to do that. I could also ask it in advance to build synonyms, but it's more efficient to have one half, the database half done in advance, which I've already done, and the other on the fly. Yeah. Yeah, but in general, that's a very good process. So what I've done is sort of, yeah. Yeah.
So what if there is a terminology or definition that is same in two different areas?
Yeah, no, so language models, a good thing is they really know natural language in the sense that they pick up things from context. Usually they will, if you ask it correctly, if the same term is used with very different meanings in group theory and topology, it knows which term is that the context is topology or group theory. This is even with common language where you have the same word. In particular, it has no problem telling apart a mathematical term being used technically and the ordinary English word being used in the same way. Yeah, so that's not, yeah. Right, so that's actually a very interesting question, and in fact this was done in the sense that fun search went, I skipped to that because I was going through many things. They actually had multiple iterations of fun search. They found the configurations that it was generating, found they had a certain symmetry to them, added that symmetry to the generating program and reran it. So since it's a little bit of Python code and not modest amount, whatever, 50, 60 lines, because it's only one function of Python code, a person can read it. And it was actually read, and on the basis of the nature of that, it was improved as well. So yes, certainly. So that is one of the things about these proofs. So the SAT solver proofs are enormous. No human can really read them. The proof of the Robbins conjecture is medium in size. It's 12 pages or something like that. Somebody printed it out. So different systems, somebody wrote it in a human readable form, and a virtuoso algebraist could have found it, or logician could have found it. So some of these proofs, especially those which are LLM generated and so on, are actually very much readable once you find them a posteriori.
Let's thank Siddharth once again for this fantastic talk. Siddharth, I think you probably have a copy of this book yourself.
I don't.
And coffee.
Oh, thanks a lot.